and welcome to the Architectural Acoustics. So as I've announced, we're going to be fully practice-led, but that won't save you from me ranting on about interesting theoretical chapters. However, they will be more random than usual. If you are interested, I have to repeat, if you're interested in a properly laid out sequence of concepts that cover the theory, please look at the videos from previous years. That's what I used to do. But I think this should be more fun, actually. So what I have as a matter of preparation are the tasks that you will be doing in the second part. Actually, we are supposed to do 2 hours per week based on some calculations, but we have a generous 3-hour slot, so don't feel pressed to stay on. In general, I will try to conclude this introductory bit in an hour, combined with theory. And then you're going to have an hour to go into groups, into different studios, and do these tasks. So actually what I'm going to do is I'm going to prepare you for doing those tasks by pretty much doing it here in front of you. Maybe not all, maybe not in full detail, but that's actually going to be the structure of the classes. So today's thing is SPL meter. Okay, it's your first device. We're not going to use it for many weeks. We're going to do measurement microphone setup. So everyone will have a box, each group will have a box of gear that will allow you to do these measurements. But today we will be fine with just the SPL meter. What does it do? It measures SPL. What is SPL? Everyone knows? Any? Sound pressure level. So why pressure? Why level? Why is it such a complex term? So I will talk a bit about that, because actually loudness is a very complex thing. So inevitably I will throw in some psychoacoustics as well, because that's the science that deals with how we actually perceive things. Now, most of the things we do will be tailored to perception somewhere down the chain, so it's always important to remember that technical properties do not map easily to psychoacoustical properties. And this includes loudness. Okay, so when we talk about loudness in terms of acoustics, we don't say the word loudness, by the way, because loudness is a psychoacoustic term. We say sound pressure level or sound level or just level. Okay, so what's exciting about this? Well, we measure it in dB. Okay, everyone knows dB, I guess. I will do some demonstration of bits. Let's see if I can fit. There's the board. I don't know if that's going to be readable at all. Maybe I will just increase the size of that for the time being. Here we go. Okay, so SPL, we measure it in dB, which stands for decibel. The actual name is bell, and this is a tenth. It's a deci, but never mind that. The point is that this is a unitless thing. Essentially, I can measure anything in dB, right? So actually in acoustics already, you probably noticed that we do dB in acoustics, but we also do it in electronic line level, right? You also say dB, and then I think what is it? Plus 3.3 volts is something. There's a few norms, by the way. So you can measure electrical current, typically fluctuating current signals, in dB. What else can you measure in dB? Well, you've probably seen it on the digital platforms that you use, that you typically have a 0 dB, right, as your maximum level, and then the level of your program is typically minus a few dB, something like this, right? Then you probably heard about peak dB, RMS dB. Things are quite complex down that rabbit hole, but I will definitely try to clear these things up. And, you know, as always, if there's anything you would really want me to, you know, maybe explain a bit better, just let me know. I will start with how on earth and what does this unitless thing actually do and mean. And my favorite examples is that I can measure age difference in dB between people, and it's much more informative. That's the funny thing, right? Because if I say, okay, I'm 10 years old, okay, and I hang out with 16-year-olds, or my girlfriend is 16, whatever, people will go like, well, that's a bit odd, isn't it? Right? But if I am, well, actually tomorrow, believe it or not, I will be 42 years old. And then if I hang out with, what is it, difference of 6 with a 8-year-old person, that's not very odd. Also, if I have a partner of that age, it's not very odd. So you see that the difference between age is not as informative as we may want it to be, because it doesn't tell me, how much older this person is. If I did this in dB, it would. Actually, if I measure age in decibels, I will get something like, well, I can get away with a partner who's more like 2 dB older than me, or younger, probably, yeah? That's the funny one. Whichever way around, the point is that a lot of things around us would be better off, we would be better off, if we measure them in dB. So what is this dB? Well, it actually tells you something about the ratio, okay? So if I want to figure out the dB difference between these age gaps, then what I do is I take the ratio. So I take the 16 over 10, and I take the 48 over 42. Anyone got a calculator quick in the hands? So you already see that this will be a far larger number, right? That makes sense. And then actually, the only difference to a proper dB would be that I take the log 10 of this ratio in both cases. I take the log 10, and I do 20 times the log 10 of that. Okay? So that's, you don't really need to remember your dB equation, but this is the crucial thing. So I'm actually looking at the ratio of things rather than their absolute distance on a linear scale, okay? And this is the way you kind of go towards the exponential scale anyway, and we will look at something very similar with frequency, right? So you probably encounter the fact that frequencies also don't translate well on a linear scale. So we'll consider that as well. Now, let's do a bit of this. How much you guys like Max MSP? Is that of any? Yeah, I see a few thumbs, a few nods, a few, what's this? That's a shake, yeah? In any case, it's not part of the, learning outcomes, but as someone who is likely to explore more than follow instruction, I hope we're, all keen on that mostly. It's good to have your tool. It's good to know your tool. And if you're exploring with sound, it could be many different platforms as well. In fact, if you're doing something acoustics, we will be using the REW, and it can produce most of the signals that I'm going to do otherwise. But I think it's a good thing, just see how it looks like. It's not that scary. And especially the bit that's not scary at all is in Max MSP is the A2dB object and the dB2A object. And it does the math, right? So I'm going to show you the math without showing you the math, essentially just the results, just to fix or to essentially explain a few things. So the point is, do I have to, just a second, that works, yeah? So what I'll do then is first I'll probably have to explain what A stands for, right? dB is somewhat obvious. So A stands for amplitude, or the way to understand this better is probably to say a scaling factor. So that's what you multiply with, right? And essentially here, my ratio is that A. So if I take the ratio, I can go to dB, right? So the ratio of 1 is 0 dB. So what does the ratio of 1 means? Means that things are equal, right? The multiplier between them is 1. And 0 dB means there's no change to the reference, right? So the very important part of the dB story is the term reference, because you cannot express decibel unless you have a fixed reference. And actually, that's the main reason why we have the dB SPL, which has a reference which is expressed in pressure. So in that sense, you see, I can only say that someone is a given amount of dB older than I am, but I cannot say that someone has an absolute age of 4 dB. One can only have a dB in relation to a reference. Okay? So that's how this is actually an evasive thing. And I don't think it takes much. It takes a few, a bit of practice, a few different perspectives typically, and then you're probably going to grasp it and be quite confident with it, because it's actually not rocket science really. So one scaling factor is 0 dB. What is 0 scaling factor in dB? What does it mean? If I multiply a signal with zeros, what do I get? Zeros, I get silence. So between a sound and a silence, what's the dB amount? And if anyone has maybe old hi-fi amps with a huge knob, and on the bottom of the scale is not a number, but minus infinity. Actually, obviously some DAWs as well, if you see the dB scale, right? At the bottom of it is minus infinity, because that's the ratio. The ratio is infinite between something that doesn't exist, and no matter how loud it is, it's already minus infinity. So that's what we actually expect from this as well. There we go. 0 is minus infinity. Okay, now typical acoustical, rules of thumb or little nursery rhymes are the doubling of amplitude gives you 6 dB difference, which also holds for putting up 2 speakers instead of a single one. Okay? So we will discuss dB in many ways. SPL dB, that's what we will measure. Now, before we go there, I just want to say a few things about the psychoacoustics of loudness. Okay, so far I have discussed the technical aspects, dB and the rest. Psychoacoustically, loudness is even more evasive. Actually, we don't perceive absolute level. What we perceive is the intensity of a sound source, which means that there's many other things that contribute. Okay? One of the things that contributes is the timbre. Okay, so if there are more harmonics in the signal, I will perceive it as louder, as more intense, right? And actually, this is fairly robust to absolute level, because if I play back a whisper really loud, you all know it's a whisper, and if I play back screaming really soft, you all get the, so to speak, musical characteristic. The perception tells you, oh, someone is screaming, right? And you don't really take on board, oh, well, it's coming through a phone, So you see, we actually relate to the timbre probably more than to the amplitude when we perceive intensity, which is actually what we perceive instead of loudness. Now, obviously, in psychoacoustics, you will have millions of very, meticulous tests, and they will tell you that you can perceive about 1 dB level difference. Okay? But that's for test signals, and that will be a huge topic for today. The point being that I have had situations where 0.3 dB change in amplitude actually made an audible difference to the mix. But add to that it went through compressor, went through other nonlinearities, a lot of things were happening, so it was more of a timbral change, right? So the thing to take away from psychoacoustics is that all the parameters that we can come up with are actually connected, even if in a very small way they are. So actually there is proof that loudness will affect your pitch perception. Obviously you have to pump huge speakers and compare it to something very soft, and the difference is just measurable, but it is the case. The loudness will also depend on the duration of the stimulus. So if you have a very short stimulus, it will appear louder, and so on and so forth. So the psychoacoustics of loudness rely on, your understanding of the timbre of the source, which means you have a reference. And the second thing is bandwidth. Okay, so harmonics and absolute bandwidth. So we're back again at the hi-fi amps. There used to be a loudness button as well. And you would think, well, why do you have a loudness button if the knob is just next to it? But the loudness button, as you may know, is a filter, which gives you a smiley EQ, pushing up the highs and the lows. And by doing that, it extends the bandwidth, the spectral bandwidth of the signal, and it gives you an impression of a louder signal. And you can even do an experiment where you have a narrow noise band, and as you increase the bandwidth, there is a certain point where suddenly in your perception the loudness goes up, whereas there was no sudden jump technically. And this relates to critical bands, which is something about the physiology of the ear. So psychoacoustics, complex stuff. But in any case, it's useful to know that we have critical bands and that we don't hear everything linearly, right? And that the bandwidth influences the amplitude, and that the level of harmonics influences the sense of loudness, and so on and so forth. And that in psychoacoustics we actually have sones and phones, which are supposed to be the way to measure psychoacoustic loudness. So I won't discuss more detail of this, just there is a huge amount of science in between the tech, the analysis of signals, and our perception, and there is no really straightforward mapping between the two. It's very complex. Okay, so how much amplitude scaling do I have to do to get minus 6 dB? Huh? 0.5, yeah. You see, so this is an interesting thing to see. So you see what I'm doing there is on the top, I'm using the same multiplier, right? And in the bottom, I get the same distance. And this will be the main thing. So whenever you try to move, also in frequency, to get the same distance, you need to have a multiplier fixed and not the difference. Okay, so you can remember the octave, right? To get an octave on top of a certain frequency, you always double by 2. So the recipe is not plus certain amount of hertz, but double or triple and so on and so forth. Okay, so this is what you can see here. So if I have 2, right, I have plus 6. If I have 4, I have 12. If I have 8, I have 18. So you see the dB value is growing linearly each time by 6 dB, while I'm actually putting a fixed multiplier up on top. What will 16 give me? 24, very good. Okay, so that's why Max is really nice, because you can see things in action. Things kind of move, and you can hear them in action as well. So I can recommend it for all sorts of experiments, and especially because part of this will now also include measuring devices, and then you roll in software and it can get much more interesting. Okay, well, dB2A, well, what we can do is we can verify certain things. 6 dB is about 2 in terms of multiplying factor. Shall we do that stupid thing? 16 by 10? See the age difference in dB? Nah, we don't have that much time. I want to be snappy. I think you got the joke. Cool. So I've talked a bit about dB. Let's see it. Okay. So here is my SPL meter. And if we all shut up, I can kind of measure background noise level, which is about 36 dB in this room. Okay? Now, what is the point about the SPL? It will be dependent on the distance from the source. That's very important. Okay? And actually, your riddle is that doubling of the distance decreases, now I'm getting confused, I believe 6 dB. I'm suddenly landed in a different universe, excuse me. I'll probably be back on track in a minute. But in any case, with the distance, you get a decreasing level. So what I can try to do is measure that, okay? So this will be part of the, actually I'm probably jumping ahead because that's task 2. So let's first talk about what am I going to measure. Okay, so the thing about measuring SPL is that it can be different based on the context. Okay, so I can measure a technical SPL, just a straight up dB value, but I can also measure A and C correction curve values. Okay, and these correction curves have everything to do with human perception. So technically, to get an equally loud signal at a base frequency, I have to push much more energy. Just practically energy, the current from the wall, it's just much more. For me to have the perception of an equally loud signal, right? And that kind of tells you why the subs are large and they consume more. And if you have a decent rig, you probably have 6 subs and 2 4 tops or something like this, because actually subs need quite a lot. And now you've seen that doubling the amplitude, so if I put 2 subs next to each other, it will give me only 6 dB increase, right? Which is not a huge amount, typically. So the point is that what I'm looking at is essentially a broadband signal, and I'm measuring that. So you probably know that noise is a broadband signal, and that we have pink and white noise as our main entrance points. What is the difference? White and pink?
White is actually flat and pink is logarithmic, isn't it?
Exactly. Exactly, very good. So white is technically flat, and pink is perceptually close to flat. So even that was very precise, in the sense that it is not the exact flat noise, which would obviously depend on who's listening as well, by the way, but it's really useful. So actually in this situation, what we want to do is we're gonna listen to pink noise and measure that, okay? So let's see that happen. I'm not saving these bits. So if everything is still good and well, are these things muted? Okay, so this is my pink noise signal. So what can I hear? Actually, I'll probably... oh, it's not even stereo. That's odd. I will need a stereo. We didn't double check that. Pan, this is left, right. Uh-oh. I believe we have a mono stereo issue here. There we go. So that's your left, my right, okay? So the point is that this is a broadband signal for audition, and if you really learn the timbre of pink noise, it can be very helpful. In fact, in Hungary, we also have a kind of a music tech course, and they actually have a module which is called a timbre solfeggio. So what they're doing as a matter of exam is recognizing noise bands, because it's something you can learn. You can actually learn to recognize something which is around 3K peaking, you know, just through your audition. And it can be useful. You know, obviously, if you're engineering, it can really speed up your EQing and potentially make it more accurate as well if you develop this. So similarly, you can develop a sense of what is pink noise like. And well, what you can try to hear out are peaks, obviously, and troughs. Okay? So let's see. I mean, I'll invite you to walk around the room a bit as well. And I will... what the hell? Did I just... There we go. So I'm playing all four. So walk around your stand up. Right? And you're not tripping as well, I hope. Yet. It's quite weird, eh? It's huge amount of timbral change. Right? As especially here, in between the ones who came here, it's like it's crazy, right? So what the hell is going on? Yes. Interference is going on. So actually the point is that if and let's do it immediately and then talk about it. So what I'm going to do is instead of playing you a mono pink noise in both channels, what I will do is I'm going to play two different noises into the two channels, right? So technically they sound the same, right? There is nothing different audibly except if you stand up and walk around. Come on. What do you think? Okay, so that's significantly better, I hope, for everyone in terms of no interference. So what we've just seen is a demonstration of what correlated sound sources do versus what uncorrelated sound sources do, right? If I play the exact same signal from the two speakers, these are correlated. And if I play two different noise oscillators, no matter the fact that they sound the same, they are totally uncorrelated. And the effect is rather different. In fact, in acoustics, we calculate the addition of level in a different way as well, between correlated and uncorrelated sources. Because what's the funny thing in acoustics is that if I have two sine waves at the same frequency, what do I get? A single sine wave at the same frequency. So sine waves don't add up like apples and pears or pints, right? you might wish that pints or like in the bar when you get the bill that the pints add up like sine waves. In fact, next time you can make a joke with I thought they added up like sine waves. What do you mean? It's like when you add two together, you still have only one to pay for, right? So that's the point, that we actually need a different intuition to develop in this domain, really. Our basic intuition, which is based on objects adding up, it's just not very appropriate for acoustics. And there will be more funny examples as well. Okay, so obviously, if I want to test the speakers, both speakers, right, in a listening situation, do I need correlated noise or uncorrelated noise? Uncorrelated. Uncorrelated between the two channels. So actually, the other thing that you might want to remember or experiment with is that something similar happens if you have a mono snare sound and you pan it middle, right? Because it's a similarly broadband signal. If it is correlated on both sides, which is typically your left-right panning center, right, then this phenomenon will occur. It will dramatically change timbre based on the position where you're at. And in fact, this thing is something that I will draw and explain in more detail in some lecture in the future. So I won't really dig into it right now. But just try to remember, and I hope this demo also kind of serves that you can remember it. Okay, so what happens then if I play a sine wave? And what I'm gonna do to keep things simple now is I'm gonna play it only through one speaker. What's your favorite frequency, guys?
448.
Oh, you fail. I've just submitted a paper, an audio paper. I shouldn't talk about this, but actually one of the punchline is you fail, because I have to, release the frustrations or the things that I hold back. Because when I was a kid, they told me many times that you failed. But instead, what I say recently is, that's not the best answer. Try again. So let's try it with a sine wave. The thing is with sine waves, I actually enjoy only low frequency sine waves. So I'll push it up to 68. I think that should be fair. So let's see if that does the trick. I still have to get used to this mixer. Mute, inst. Does this happen as well? Sorry, let's see what's going on here. So we had, oh, come on, what happened? Save that, quit that. Otherwise I'll just slash up a sine wave online somewhere. So the point with the sine wave is, does everyone know what the sine wave is very special for? It is the narrowest bandwidth signal that we can conceive of. And an actual sine wave is a sine wave only if it lasts forever. It's like true love. As soon as it terminates, even after thousands of years, a sine wave is not a pure sine wave anymore. Just for, spicing it up a bit. That's the scientific background of it. In fact, if I shorten the sine wave, the shorter it is, the broader the spectrum. And if I shorten it down to a single period, going up and down once, the spectrum is quite flat. In fact, at that stage, you can't discern the frequency. You actually need a few cycles to get the frequency perception going, right? So if you really, really shorten the sine wave, it becomes an impulse. And an impulse also has a flat spectrum itself, okay? So that's this interesting kind of transition there. Let me see if this thing came to life in the meanwhile. I have no clue what's going on. Okay. Oh, this sounds like my clicks, is it not? No, I've probably messed it all up now. Well, at least you're gonna listen to some sine waves. In any case, I'll just talk about it. I won't waste the time with fixing this at this stage. So what happens with the sine wave, right, is that you will actually hear how that frequency lives in this space, or the space when you start listening to it, and you will discover that based on your position, this will hugely change. The amplitude of this sine wave will change in different points in the room. Okay, so it also goes back to this metaphor, I hope it's memorable, that the acoustic space is a bit like 3D ocean surface. Okay, so that's the complexity you expect, and it's much better attitude than thinking, oh, well, these are like, arrows coming out of the speakers and coming in here, and that's just not a great model of how sound operates. So I will suggest you listen to sine waves and then to sine sweeps. Now, actually, I'll probably leave this to you guys just to discover and discuss in the groups. I will trust you. You are mature enough to just source your own sine sweep. You can strike up REW already and listen to that. But on YouTube there will be, you know, sine sweeps, so it's not a big deal really. The two things that you can listen in a sound sweep are the amplitude fluctuation, okay? So if you listen to the sine sweep going from very low frequencies to very high frequencies, you will hear the amplitude going up and down, okay? This is a combination of the speaker, the room, and the location of the speaker and the location of the listener in the room, okay? So if any of these four things change, it will be a different trajectory, okay? So it's a very sensitive thing. Now, it can be useful, very useful, to identify really odd peaks, okay? So in fact, what I would suggest, and I'm not sure if I have enough hands in the air, I'll maybe just make a max patch to kind of do this quickly. Although I do think that it really, you know, puts you in the good mood if you have to source these things yourself and kind of, let's find it, you know. In fact, you know, it's a kind of I think it's a fact about learning that if all the things are available, you will never go through all of them. Actually, table of contents is counterproductive. So it's much more motivating to be in a labyrinth, you know, and you're kind of going forward. Okay, do I take the left turn? Do I take the right turn? You know, it's a kind of an immediate thing. Whereas if you have the overview, and these are all the things that you're going to do in the next 3 years, you know, then it's a bit of a drag, really, because like, yeah, but okay, now I know what I'm going to do, and half the fun is gone with, right? So actually not knowing how you're going to do things and finding your way, you know, is really, really a good way of going forward. So try that. If you struggle, I will help you, obviously, and we'll do this together. So the amplitude trajectory. If you hear a great peak, you can actually pinpoint it, and if you have it on a dial or with a display, you can know which exact frequency that is. Okay, so that can be very helpful. Same holds for the dips. Okay, so what happens in the acoustic space when we have speakers projecting sound is that depending on the positions, you will have peaks and dips. It's just a matter of fact. Okay? So that's one thing. The second really important thing, which actually tells you something about the speaker only, is the timbre of the sine wave. And I don't know why, but this is just not really out there. People don't tell you to listen to the timbre of the sine wave as it sweeps. But actually, with your ear, you're very able to discern the level of harmonics, especially if you build in, you know, if you kind of work on your internal silkiness sensor. I would say that the pure sine wave is the silkiest sine. And as soon as it gets a bit of an edge, a bit of a character even, you know, it actually means that there's harmonics cropping up. So why do harmonics crop up? And this is the actual topic of the final lecture in late December, which is hopefully going to be very soothing, is that as soon as you have a nonlinearity, you get harmonics. Okay, we will dig into this a bit more. I'll try to explain it with, you know, interesting metaphors as well, but probably it's worth kind of, you know, solidifying the foundations here. So if you imagine a pendulum, right? A pendulum without friction will go on forever, right? Now, a pendulum which has a totally non-elastic suspension will give you a sine wave. But if there is a nonlinearity in the suspension, if it is a spring or just a non-ideal material like everything, right? Then you have a nonlinearity. What is the nonlinearity about? Well, typically, you can imagine that when the pendulum swings away, it pulls on the cord more. And when it pulls on the cord more, if it manages to stretch it a bit more, that is your nonlinearity. And if you plot that and you compare it visually with a sine wave, you will not see a difference. It's such a minuscule, you know, rounding off in one way or the other. But if you plot the spectrum of the actual sine wave, there is not a single harmonic in there. If the sine wave went through any amount of nonlinearity, you will see harmonics crop up. Okay? So that's the point, that if you learn to listen to your sine sweep, you can identify where does the speaker distort. Because that's distortion. Nonlinearity, the yielding, the harmonics, the cropping up of the harmonics is distortion, nonlinear distortion. Okay? So you can actually listen to the distortion of the speaker. And in my experience, well, I don't want to push it anyway, but ATCs are not the silkiest, but they're really consistent. You know, the timbre of the sine wave, actually I shouldn't be saying anything about it to you beforehand, because I'm priming you, and psychoacoustically this is a no-no. I'm not supposed to tell you what you're going to hear, because that will, you know, help you hear it. Never mind that. You will hopefully listen to quite a lot of sine sweeps. You will. So with the ATCs, it's very consistent. It has a bit of a sharpness to it, but it's just consistent throughout the spectrum. Whereas, for example, my ProAx, they have a few, you know, problems along the spectrum, but at times you get the silkiest sine wave. You know, it's just a really, really pure thing coming out of it. Technically, we cannot produce a perfect sine wave with analog equipment, believe it or not, because there is always some nonlinearity. So the fact is that the digital sine waves are much purer than the analog ones. You know, so don't confuse the synth building wisdom, which says get an analog oscillator, with your precision instinct, which knows that an analog sine wave will have some harmonics. It will never be a pure sine wave. Okay? So that's what I suggest when you come to listening to a sine wave, sine sweep, you know, listen to the, and then comes my favorite, which is a noise band sweep, which is also not out there, really. I'll probably just put a link on Blackboard while you're walking to the studios, because I've put out a YouTube video with it, because it's just not out there. And what I have there is octaves band worth of noise, which is sweeping up. So it's a kind of a sine sweep principle, but it's not a sine wave sweeping up, it's a whole band. And it was mesmerizing that when I discovered that, for example, Genelecs have a horrible noise band sweep. And it kind of tells me that they're tuning it on time alignment and not on frequency response. These two things are in a bit of a love-hate relationship. It's a bit of a trade-off, one or the other, right? Whereas, for example, ProAx have a beautiful, beautiful noise band sweep, okay? So I'll just invite you to listen to it. The interesting thing that I didn't anticipate, I mean, I anticipated that it will give me a better sense of smoothness of a speaker, because when I listen to a sine sweep, I kind of hear it going up and down in amplitude, but I don't really have a plotter in my brain that gives me something that I can overview at the end of it. You know, and I do think that I'm just not reliably able to, you know, say that, well, this is a worse and this is a better one if they're close together, because, you know, how much did it go up, how wide were the gaps, the peaks? It just doesn't compute that easily. But when you hear a noise band sweep, you get a really good sense of how smooth it is in the bass, low bass, mid, as it goes up. It really tells you quite a lot about the speakers and the room as well. It's a combination of the two, right? So it's worth repeating. Only if you detect harmonics are you looking at the speaker only, because room is a linear system. It will never add harmonics to the sound that is emitted. It may change the spectral characteristic of the signal, evidently. It may change the time characteristic of the signal, right? If I clap, you know, here and there, it's a different duration. But those are both linear time invariant properties. The nonlinear property is the distortion, the arisal of harmonics. Okay, cool. And then, well, I'll probably upload this patch as well. I just don't want to waste time with trying to hack this. So we have a pulse train to listen to as well. Now, the pulse, as I said, is a broadband signal. In fact, it has a flat spectrum technically. Now, the interesting thing is, or the worthwhile knowing thing is, that we can't put enough energy into an impulse for it to be worth using in measurement. Okay, so actually a sine sweep is just like an impulse because it has all the frequencies. That's a horrible thing to say, but let's go for it. But it is stretched in time, which allows me to put more energy into the signal. Because the thing to note about signals, I mean, it's a kind of rule of thumb or a bit of a, worth knowing, is that you can estimate the energy of the signal how? Anyone knows? So if I have an audio signal which goes something like this, and I have an audio signal which goes something like this. Let's try to make it a bit more like that. So the interesting thing between these two signals is that this one has more energy and this one has a higher peak. Okay, so seeing the peak of a signal is fairly straightforward. You get that. Seeing the energy is actually not much worse because what you're looking at is the surface area enclosed by the signal. Okay, so the surface. So actually, if you compare a sine wave to a square wave of the same amplitude, you know for sure that the square wave has more energy. Okay, and if you compare it with a pulse wave of the same frequency, then you see that an impulse carries very little amount of energy. So no matter how hard I push it, it will still be far, far too soft for using in measurements where there is a noise floor or there's some intermittent issues as well. Okay? Now, nevertheless, the pulse train is quite useful because what it does, it stops abruptly. Okay, so it allows you to listen to the ring. To the response. You can actually hear, well, we'll see how loud you can drive it. In fact, while you're out there, maybe obviously I'll have to work this out. It's the first lecture. It's a new setup. But I might be able to play a decently loud impulse wave or pulse wave with these 4 speakers at the time. Okay, so that will be the first task. So check out these analytical signals, listen to them. And then we have 2 tasks with the SPL meter. So the first one will be measuring pink noise at 1, 2, and 4 meters away. Okay? Away from the source. When the source is, number 1, in the middle of the room, against the wall, and in the corner. Okay? And then, you'll see typically what happens is that people, make a group with someone they're already familiar with, and typically the groups stay more or less the same configuration. But I can invite you, to just mingle a bit more as well. And typically what happens is also that the kind of task division happens within the group. There's always someone who loves admin. It's fun, it also gives me, when when I'm inspired for admin, it means that I'm putting my subconscious in order, everything's gonna be, although I do prefer disorder for most of my days. I have my days of order as well. So someone probably best off, noting these down, and then we'll probably collect them and look at them briefly at the beginning of next lecture. Okay, because some groups work faster, some slower, we will not reconvene here. By the way, at 5 o'clock, if you're bringing your tracks, we will. So the Yamahas are staying for our track attack. We'll see if that happens. So do that when the speaker is in the middle of the room, speaker against the wall, and speaker in the corner. And there should be, obviously, differences. I advise you, right, to keep the level coming out of the speaker the same. Okay? And then once you're done with that, then you can try to draw a polar response of a speaker. So what we have here in the kit, we have a speaker, you have a sound card, which will allow you to hopefully connect to your laptop, but in some studios there is a sound card, so that's optional. Then, is that us? No, probably not. And then we have the SPL meter, which I've just taken out. I'll put it back in. And you're also supposed to have in the kit masking tape and a pen. I see it there. I'm not going to dig it out. So what you can do then, you're supposed to, in task 3, put the speaker in the middle of the room, and you're supposed to find 8 measuring positions in a circle around the source at 1 meter. Okay? So if the speaker is here, what you can do is you can locate, well, you're supposed to locate the center of the membrane somewhere. So you can take this axis and you can mask tape from there, right? You can take 1 meter and then you can make a cross there and do that 8 times in the round of the speaker, right? And then, well, you just, as much as you can, you know, stand above that point and measure the response there. Okay? So that's the idea. Try to get a polar response. I ask you to produce a table of results, but actually, if you're really artistic, or inspired at least, what you can also attempt to is draw a polar response. You've probably seen a few polar responses already. So the thing would be then, I'll just briefly show you how it should look like. So you have a circle, and then there should be 4 more points. Obviously, it could be more precise, right? So these are your 8 measurement points, and then you can measure out the dB value on each line. Okay? So typically what you expect is that you will get, if you get maybe 78 dB here, right, that this value will slowly keep decreasing and you will get something like this. Right? That could be your polar response. So the distance from the center depicts the amplitude, the level, sorry, at that point. Okay, so you can do this. And if you really want to stay on and you're having too much fun anyway, what you could try to do is make a polar response at multiple frequencies, right? Because the matter of fact is that this could, if this is, let's say, 5K frequency, the maybe 50 hertz frequency will not exhibit much of a polar characteristic. You will measure pretty much equally all over. Okay, how cool is that? All right, so check out the rooms, get into groups. In fact, one group can stay in this room. I already have the gear, okay? And then I'll be walking around and just helping you out. And I will upload this to the Blackboard promptly, together with the link for noise band sweep.